There's a story that goes around, nobody knows if it's true or not, of a math teacher who was really tired of grading exams. The teacher got the bright idea to make a one-question calculus exam. But what problem should be on the exam? How about the easiest calculus question ever? But it should still be important. How about what is the derivative of e to the x? Of course, if you know calculus, the answer is e to the x. It is the easiest possible question. But imagine being a student in the class. You come to the final exam, you see it's one question. What is the derivative of e to the x? You would be sweating. Is this a trick question? Is it really e to the x, or am I forgetting? Some students finish just like that, and some students sit there sweating the entire time. In this video, we're going to talk about the derivative of e to the x and also the derivative of b to the x, where b is an arbitrary base bigger than 0 but not equal to 1. These are derivatives of exponential functions. We start with a partial derivation of the exponential function derivative rule. Let b be positive and not equal to 1. Actually, what we do does apply when b equals 1, but it's not interesting. The function is b to the x, and if b were equal to 1, that would be 1 to the x, which is always 1, a constant function. The base b is constant. The variable is in the exponent. That's an exponential function. Part A says use the limit definition of the derivative to show that f prime of x equals c times b to the x power. In other words, the derivative is a constant multiple of the original function itself for some constant c. Part B says what is the value of that constant c. I'm just going to tell you the answer. Maybe you already know it. I'm not going to prove it. I'm not going to derive it. That's beyond the scope of this video. All right, start with part A. F prime of x, by definition of the derivative, is the limit as h goes to 0 of a difference quotient, which represents a slope of a secant line, and then again the limit represents the slope of the tangent line, to the graph of f at the number x. This is the limit to compute. We don't know what b is. You might say, is this possible to even do? Well, it is possible in the sense of the directions in the problem. Let's see what happens. So first we need to find f of x plus h. Go to the formula for f of x and replace x with x plus h. You would get b to the x plus h. Subtract f of x itself. That means subtract b to the x, all divided by h. You look at this kind of thing, it looks pretty scary, like I have no idea what to do. So far the examples we've done, we've ultimately been able to cancel things that don't involve an x on the top, factor out an h out of the remaining terms and divide it out with the h on the bottom. But how can you possibly do that here? All right, well, don't panic. Again, we're not going to be able to fully do the answer. I will again tell you what c is, but here initially we just need to try to simplify it as best we can. One bright idea you might have is to say, well, maybe I should try using a property of exponents in reverse, so to speak. B to the sum of two numbers is b to the first number times b to the second number. Maybe that's useful. I mean, again, that's the opposite direction of the way we usually use that property. We usually start with something like this and say, add the exponents to get this. But they're equal. We can go backwards too. This does have the benefit now of the fact that both terms in the top have a factor of b to the x, and whenever you see something like that, you should think to yourself, oh, I could factor it out. Maybe that's useful. So go ahead and factor b to the x out like this to get b to the x times, in parentheses, b to the h is what's left there when b to the x is factored out. What's left here? Minus 1, right? Because negative 1 times b to the x is negative b to the x, all divided by h. Doesn't look a ton better. What should we do now? Remember where you're trying to get. You're trying to prove ultimately that f prime is some constant c times b to the x. I do see a b to the x there by itself. And when you compute this limit, you treat x as if it's constant and treat h as the variable. With respect to this limit, that's a constant right there. We can use a property of limits that says constants can be factored out in front, and that would provide the b to the x. So let's go ahead and do that to get b to the x times the limit as h goes to 0 of b to the h minus 1 over h. It's looking better, but where's the constant? This is the constant. That's c. The constant I'll now write in front with parentheses as a limit as h goes to 0 of b to the h minus 1 divided by h. That is the constant c that gets multiplied by b to the x. Now, I'm really not proving things. You might wonder, does this limit exist? How do I know it exists? Well, you could try to provide graphical evidence for yourself by trying different values of b, plugging in different values of h, and seeing that we seem to be approaching some constant. You could also make the graph of this function of h. It does exist and does equal some constant. And yeah, let me now tell you what that constant is. Because part B says, what is the value of the constant c? It turns out that the constant c is the natural log of b. Isn't that wild? C, this constant, this limit, does exist, and it turns out to equal the natural log of b. We're not proving it, I'm just telling it to you. You need to accept it. And what this all implies now is ultimately our derivative rule for exponential functions. The derivative with respect to x of b to the x power turns out to be the natural log of b, that's a natural log of b, times b to the x. There we go. That's our derivative rule for exponential functions. Think about it in the case where b equals e. This would imply the derivative of e to the x is natural log of e times e to the x, but natural log of e is 1. You get 1 times e to the x, just e to the x. So I can write, so the derivative of e to the x, where e is the special number that's about 2.71828, blah, 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 is natural log of e times e to the x, but natural log of e is 1. In the end, you get e to the x, and there's your easiest calculus question ever. And it is true, and it is a very fundamental, important fact in calculus, okay, that you should know. It turns out to prove all this, it's actually better to define logarithms in terms of integrals and then use facts about inverse functions. That's not the topic of this video. Number 2 is kind of a tricky derivative question where we are trying to decide whether the exponential function derivative rule that we just derived and or the linearity of the derivative property that we talked about in the previous video can be used to compute the derivative of, for example, in part A, this function, in part B, it's this function, and in part C, it's this function. If so, go ahead and compute that derivative, and if not, kind of try to explain why not. I will try to do that, though it's not part of the directions here. All right, part A. It doesn't look like we can use the exponential function rule plus, well, I should say, facts from the past, such as the power rule that was in the previous video too. All right, so what do we have here? We've got, is that an exponential function there? We've got some powers, some exponents. No, because the x, that's the variable, is in the base. This is not an exponential function. This is a power function. We need the power rule from the previous video. Go ahead and take that derivative and also use linearity because we have the sum of two functions here. The derivative of this function f will be the derivative of the first term plus the derivative of the second term. And the second term has the x and the exponent. This is an exponential function. The base is pi squared. Realize that when you see this kind of notation, pi squared needs to be computed first before you take x and raise it to that power. That is the n for the power rule. So the derivative says you'd bring down that n, which is pi squared, and then you'd subtract 1 from the exponent. You'd have x to the pi squared minus 1 power. Now you could go ahead and use your calculator to approximate pi squared. That's kind of beside the point, but if that makes you feel better, you certainly could do so. That's the derivative of this first term, x to the pi squared power. And yes, this is an exponential function right there. Base is pi squared. So by what we just derived, it's natural log of the base, which is natural log of pi squared, times b to the x, pi squared to the x. Okay? You could multiply those exponents. You could write this as pi to the 2x. You could also bring this 2 power in front and write it as 2 times natural log of pi. It's not a big deal. This is possible to do. We've used these rules plus the power rule to do part A. On to part B. Can the exponential function derivative rule and or linearity of the derivative and possibly the power rule be used to compute the derivative of this function now? Okay, so this does look kind of like an exponential function. We got a base of 2, but the power there is more complicated. It's 3x plus 5 instead of just an x. Maybe we should try to rewrite that function first. That's a big hint that yes, this is possible. We've got the sum of two things in the exponent, just like in the previous problem. We could break that apart like this. 2 to the 3x times 2 to the 5th power. 2 to the 5th is just constant. It can be brought out in front when we take the derivative just by the linearity rule. And 2 to the 3x, how about that? That 3 seems to be messing things up. However, we can use another property of exponents to write that as 2 cubed to the x. Of course, 2 to the 5th is 32, and 2 cubed is 8. So this is the same function as 32 times 8 to the x power. I haven't taken any derivatives yet. I'm just rewriting the function in a form for which I can now use our rules. Linearity implies that 32 just gets carried along for the ride. And then you have, that's an exponential function, 8 to the x. The base is 8. We would get natural log of 8 times 8 to the x for its derivative. Okay? And that's probably the simplest way that you can write it. And that would be the derivative for part B. Part C, can the exponential function derivative rule and the linearity be used to compute the derivative of this function? If so, compute it. All right. That is an example of something where you cannot compute the derivative. Why? 3 to the x squared, that is the same as 3 to the quantity x squared, meaning when you plug a number in, you'd first square it before you make it the exponent of 3. And yeah, you could rewrite this in other ways. You could write it as 3 to the x times x, and you could write that as 3 to the x, but there's no way you can write it as some constant times the base to an x power just by itself. And that's enough to imply that we cannot compute the derivative of this with any rules that we know so far. That is the answer. It's not possible with those rules. It is possible if we know some more rules, in particular something called the chain rule, but that's a topic for another video. Doesn't number 3 look like fun? Let f of x equal this entire thing, this linear combination of a bunch of, well, a power function there, exponential functions, the product of exponential functions, we don't know the product rule yet. I'm not saying is this possible. It turns out it is possible. We need to use another property of exponents. These three terms involve e to different powers and a constant there. This involves pi, and that's e. That e is just e by itself. It is a constant. There's no x. The derivative of that will be 0. That's the easiest part. What about the rest? Use linearity. Take the derivative of 2 times x cubed. You'll get 6 times x squared. Subtract the derivative of 7 times 3 to the x. The 7 gets carried along for the ride. The base here is 3. This will be natural log of 3 times 3 to the x. How do we do this? We don't know how to differentiate a product in general. However, by a property of exponents, we can write that as 10 to the x. Okay? That's a property of exponents that you can do. You can combine the 2 and the 5. 2 times 5 is 10. Get 10 to the x. And then we can differentiate that and get natural log of 10 times 10 to the x. Keep going. The derivative of 4 times e to the 2x, write that as 4 times e squared to the x if we want to avoid the chain rule, which we do want to avoid so far. The derivative of that will be plus 4 natural log of e squared times e squared to the x. Natural log of e squared is 2, so this becomes an 8. And we can re-simplify this to e to the 2x if we like. Similar kind of thing can go on with e to the negative x. It's the same as e to the negative 1 to the x. Differentiate that. You are going to get natural log of e to the negative 1 power times e to the negative 1 to the x. Natural log of e to the negative 1 power is negative 1. This all becomes minus e to the negative x. Then the next term, the base is pi, so we get plus natural log of pi times pi to the x. And then again, the derivative of e with no x in there, with respect to x, is 0. This is just a plain old constant. So this is the derivative, and yes, you can simplify this to 8e to the 2x and simplify this to negative e to the negative x. Number 4 is kind of a strange question, but really important in Calculus 2 and in applications of Calculus 2. Find a quadratic polynomial, g of x equals a times x squared plus b times x plus c, which best fits the function f of x equals e to the 2x at x equals 0. If those are your only directions, it'd be like, what in the world am I supposed to do here? But there are more directions. What does it mean to best fit the function f of x equals e to the 2x at x equals 0? It means they have the same function value at 0, g of 0 equals f of 0. They have the same slope at 0, g prime of 0 equals f prime of 0. And they have the same amount of concavity, you might say, g double prime of 0 equals f double prime of 0. We also want to use technology to graph these in the same set of axes and see what we notice. So it's a matter of just ultimately doing some algebra here. Figure out, first of all, g of 0. Plug in x equals 0 into this, you're going to get c. F of 0 is e to the 2 times 0, is e to the 0, is 1. We want these to be equal to each other. We're going to set these things equal to each other and solve for c. This implies c must be 1. Okay, so we found c. What about the derivative? G prime of 0 should equal f prime of 0. We better figure out those derivatives first. G prime of x, g is a polynomial. A, b, and c are constants there. The derivative of ax squared is 2ax. The derivative of bx is b. And the derivative of c with respect to x is 0. What about f prime of x? F of x is e to the 2x. As we saw in the previous problem, we want to write that as e squared to the x and use e squared as our base. Again, we're not assuming you know the chain rule yet. So the derivative would be natural log of e squared times e squared to the x, which can be simplified to 2 times e to the 2x. Interesting, the 2 kind of gets brought down. It's not the same as the power rule, though. Don't get that confused here. All right, so what is g prime of 0? Plug in x equals 0 there, you'll get b. What is f prime of 0? Plug in 0 here, you'll get 2. E to the 0 is 2 times 1 is 2. We're setting these equal to each other. And once again, we have a very simple equation to solve for b. It's already solved for b. b must be 2. And then we go on to the second derivatives. G double prime of x. Differentiate this with respect to x. You get the constant 2a. Parabolas have constant second derivatives. F double prime of x means we have to take the derivative of this. The 2 in front gets carried along for the ride. And what's going to happen when you differentiate e to the 2x is you get the same thing we got before, 2 times e to the 2x. So we get an extra factor of 2 in there. This derivative is ultimately 4 times e to the 2x. And then we want to plug in 0 again. G double prime of 0 is 2a. You don't see any x's there. That's a constant. It equals 2a no matter what x is, but in particular when x equals 0. F double prime of 0, looking at this formula, is 4 times e to the 0 is 4. We are setting these two things equal to each other. And we have to do a tiny bit of work here. We're saying 2a equals 4. We do have to divide by 2 to say a is 4 over 2, which is 2. So the answer to the question, find the quadratic polynomial which best fits this function in this sense here, the answer is that g of x is ax squared plus bx plus c. A is 2, so we get 2x squared. B is 2, so we get plus 2x. C is 1, so we add 1. So there's the answer to finding that quadratic polynomial, but we also want to use technology to graph these things on the same set of axes and describe what we notice. Okay, so go to the calculator. My y equals screen, I'm going to plot e to the 2x. I'm plotting both functions here. And I'm also going to plot this function that is the answer, 2x squared plus 2x plus 1. It's supposed to fit it near x equals 0. What happens near x equals 0? Let's try negative 2 to 2 just to see what we see. Function values at 0 are 1. So maybe let's try negative 1 to 3 and see what we see. Graph it. Here is e to the 2x. And then the next graph that we see there is the graph of the quadratic. And we see that they match pretty well near 0. That's what we observe. They have the same function value, the same y-intercept of 1. They have the same slope at x equals 0. Right there. What is that slope? You could Differentiate this, get 4x plus 2, plug in 0, you get 2. The slope of the tangent line there is 2. And they have the same amount of concavity, you might say. Same curvature, you might say. Different ways to describe the same thing. Near 0, not elsewhere. This quadratic function is a good approximation to the exponential function when x is close to 0. Our last problem is about exponential decay in the context of car depreciation. The value of a car bought in 2022 is given by this function, this exponential decay function. V of t equals 35 times 0.88 to the t. The fact that this number is between 0 and 1 is going to mean this is exponential decay. The derivative is going to be negative in value. T is time in years from the date of the purchase, and V of t is the value in thousands of dollars. Part A says, evaluate and interpret V of 2, including units. No calculus there. That's just a function problem. Plug in 2, this is time in years after we bought the car, so in 2024. 35 times 0.88 to the second power, replace t with 2. Order of operations is really important. Do 0.88 squared first. Powers get done first. To get 0.7744 times 35 gives you 27.104. You might round that to 27.1. What are the units of this? This would be thousands of dollars. They are units for the output of the original function. How does this get interpreted? It's the price. It's the value of the car 2 years after you bought it. Is it right? It may not be. We are modeling. This may not be the true value. That's determined by the market. It's an approximation. Part B. Find an expression for v prime of t. Okay, so we need to differentiate this exponential function. Even though it's exponential decay, it's still exponential. The base is 0.88. The 35 gets carried along for the ride. Natural log of 0.88 needs to get in there, times 0.88 to the t power. There is the derivative. I said the derivative should be negative. That doesn't look negative, does it? Well, guess what? Natural log of a number between 0 and 1, like 0.88, is negative. Okay, so this does have negative values. Let's go ahead and do part C. To see a particular negative value, evaluate and interpret v prime of 2, including units. So we plug in t equals 2. We get 35 natural log of 0.88 times 0.88 to the second power. We already did 0.88 to the second power times 35. What's left now is to multiply by natural log of 0.88 to get a negative number for the answer, about negative 3.465. Negative 3.465. If you're interested in what is the value of natural log of 0.88 itself, it is about negative 0.1278. Okay, so this is negative as we expect for an exponential decay function. What are its units and how do those units help us interpret it? Units would be units of value of the car per unit of time. Units of the dependent variable per unit of the independent variable. Thousands of dollars per year. But how do you interpret that? I'm not going to write it out, I'll just verbally say it. This is a rate of change. It's approximating the rate of change of the function at t equals 2. It is, in fact, the exact instantaneous rate of change there. The graph is decreasing and concave up. It's exponential decay. The slope of the tangent line there is about negative 3.465. This is the ideal linear approximation. If we let time go a little further, like 1 year, we would expect the value of the car to go down by about $3.5 thousand. Since its value at time 2 is about $27,000, we would expect that at time 3 the value would be in the ballpark of $23.6 thousand. That's what the linear approximation would give us. Is it going to be too big or too small? The linear approximation, the tangent line is below the graph because the graph is concave up. It's going to be too small. The value will be a little bit bigger. What is that value? Let's just go ahead and compute it to end the video. It would be 35 times 0.88 to the third power. The calculator knows to do order of operations with the power first. And yes, it's a little bit bigger than 23.6. It's about $23,850. Thanks for watching.